Welcome to another video lecture. In this lecture, we're going to be taking a look at antiderivatives for the first time. This is the last section of material that we'll be covering this semester, so you can sort of rejoice in that. We are almost done. We'll be covering section 4.9 here over the next two class periods. Wednesday's lecture, I'm recording on Tuesday, but that'll go up on Wednesday, and then we have Friday's lecture. Both of those topics are needed for the quiz that is due on Friday, April 24th at 11:59. That quiz will cover antiderivatives. I believe the practice quiz is already up for that. This is quiz 11, by the way, so I should mention that I will only keep your 10 highest quiz grades, so one of your quizzes will be dropped. So if you're sitting at this point of the semester and you have 10 really good quiz grades, then this one isn't all that important in terms of grade, but I would still recommend you go ahead and do it and try your best as a preparation for next week's exam. So we will be having an exam next week. The exam is currently scheduled for, I believe, Monday. And I do want to keep it on Monday because you have your final calc labs that I'm going to give you the day off next Wednesday to finish working on. And then we'll talk about the final exam next Friday. But for this week, just the things that should be on your radar. Continue learning more about optimization from Monday. Learn all you can about antiderivatives, which will be Friday's quiz. And then you have homework over optimization and antiderivatives that's due this Sunday before the exam on Monday. So let's just jump into it. What I want to take a look at here this morning is just an introduction to what an antiderivative is, what are some of the rules that you need to be aware of, how does this relate to derivatives that we've talked about in this course. And I just want you to understand this is really an introduction to Cal 2 at this point, because in Calculus 2 you spend the entire course dealing with antiderivatives rather than derivatives. We've spent most of the Cal 1 course dealing with derivatives, but that won't be the case in Cal 2. Cal 2 will have some derivatives, but it'll be mostly antiderivatives. So we're going to start with the definition. If you have a function, we'll call it capital F here, that function is an antiderivative of little f if the derivative of the antiderivative is the function. In other words, we know that the derivative of x squared is 2x. So this tells me that the antiderivative of 2x is the function x squared. In other words, if you take the derivative of x squared and get 2x, then to go backwards requires the antiderivative. That's sort of the opposite here. This function is the antiderivative of the function x squared because the derivative of x squared is 2x. Okay, that's just sort of the definition that we're using here. And I struggled to figure out a way to notate this. I just wrote down antiderivative as a word. We don't want to keep doing that. So we need to have some sort of notation for this. And our notation for this is this symbol here, which is known as the indefinite integral. We'll only deal with indefinite integrals in this class, although in Cal 2 you'll deal with something called the definite integral. But you should really just think of it in this class as being antiderivative. So this symbol means find the antiderivative of the function little f, and we know that the antiderivative based on this definition is this function capital F plus c. And I should mention the reason for the plus c. If you use the definition right here, then that says that the derivative of your antiderivative should be the little function f that's inside the antiderivative here. So notice that if you take the derivative of this quantity on the right-hand side, the derivative of the antiderivative, well, the derivative of capital F is f prime, but according to this definition, that's little f. And then the derivative of c, a constant, is 0, so it doesn't show up, so you get f of x, which means anything over here you can add a constant to, and that's still an antiderivative of the function f. So this would be f prime of x plus 0 equals f of x, which is still true regardless of what c was. So when I said that the antiderivative of 2x is x squared, I could have also said the antiderivative of 2x plus 3 is x squared, and the antiderivative of 2x minus 5 is x squared. All of those give the same antiderivative, which can be a little problematic because there are two types of antiderivatives. You have what are called general antiderivatives, which involves that plus c on the end of it, and it can be any infinite number. It's a family of antiderivatives. Or you can have what are called particular antiderivatives, which is you have some particular function that you're looking for, and this is when you've solved for c. We're going to show off both cases today in this lecture, but I just wanted to make sure that you understand some of the notation and language that we're using here. So when we write the integral form like this, the function f of x that's inside here is called the integrand. And then this dx is what we're taking the derivative with respect to. You normally the d. So think of it this way. When we take the derivative of a function, this is our operator that tells us to differentiate with respect to x, with respect to the function x. Well, the notation here is for the antiderivative is the antiderivative operator. So both of these are a part of the operator that tells you to integrate or anti-differentiate with respect to x as well. If you have a different thing here other than dx, then you're integrating with respect, or anti-differentiating with respect to a different variable. And the thing is, the reason that we have that here is because if you take this and plug it into this, you get df dx. You can see that the dx cancels here. And it's simply just the integral of df, and d is really the derivative operation, so the antiderivative of the derivative. Those two cancel out, leaving you with just f of x, which we know is what should happen there. If you take the antiderivative of the derivative, those should just cancel out and give you the function f. It turns out it gives you the function f of x plus a constant, like we've talked about here so far. But that's the reason, or one of the reasons for the dx being there, is so that notationally this makes sense. There's actually a deeper reason for the dx to be there, and you'll talk about that deeper reason in Cal 2. All right, so let's look at the most basic antiderivative rule that we can start with, and that is the power rule. So if you recall the way that we did the derivative, the very first derivative formula we learned was power rule, and we said that the derivative of x to the n is nx to the n minus 1. Okay, so think about what it would take to undo that, because the antiderivative would undo that. So if I had the antiderivative of x to the n, what would that entail? So I'm going backwards. So normally I would multiply by the power, but it's the power, so here you have n minus 1 as the power because you'd subtracted 1. So I would be wanting to divide by n, which was the previous power. So I want to divide by the previous power. And if I'm looking at x to the n, the previous power is n plus 1. So I would want to divide by n plus 1. And then rather than subtract 1 from the power, I want to go back to that previous power, which is n plus 1. And then remember plus c, because you get all possible antiderivatives that way. So this should make sense as the power rule, I have it written right here. Let's just take the derivative of it and make sure we get back. If you take the derivative of x to the n plus 1, notice what happens here is you get n plus 1 to come down, x to the n plus 1 minus 1, and then you're dividing by n plus 1. So what ends up occurring there is the n plus 1's cancel, 1 minus 1 cancels, and you're just left with x to the n. So this is indeed the correct formula, because if you take the derivative of our antiderivative, you get back to the original function, which is the integrand xn. All right, let's do some examples here. We're going to do several examples today to get you comfortable with this. So I want to find the antiderivative of this polynomial. So we're looking at the antiderivative of x cubed minus 1/2 x squared plus 2x minus 4. So this is the way that you would notationally write this. And you know, one thing that needs to be discussed here is I've got multiple functions going on here. So how do I take the antiderivative of multiple things? This is just the formula for the antiderivative of one thing. And if you recall, the derivative of f of x plus g of x was the derivative of f plus the derivative of g. In other words, the derivative as an operator distributed to each function that you were being asked to differentiate. The same thing is going to be true here. The integral operation or the antiderivative operation will distribute to each function. So this is going to be written this way. It's the integral of x cubed dx minus the integral of 1/2 x squared dx plus the integral of 2x dx minus the integral of 4 dx. So you would distribute the integral to each piece. Now, upon doing so, notice that some of them still have constants inside. Like there's a 2 inside here, a 1/2 inside here. So I don't have it exactly the integral of x to the n, but also going back to derivatives, remember that the derivative of a constant times a function is the constant times the derivative of the function. So that gives me hope that I can do the same thing here, which in fact I can. You will prove all of these things in Cal 2, but we're just going to introduce them today. So for this integral here, which has a constant of 1/2, I can factor that constant outside the integral and then just take the integral of the function. I can factor the 2 outside and so on. And here I'm actually going to factor the 4 out since it's a constant, and that's just going to leave me with dx. And there's a point that I want to make about this, but I'm going to factor the 4 out and leave this the integral of dx. Okay, so now we're going to apply this rule. We're going to apply power rule. All right, so this is the rule I'm going to apply. We have x cubed, so xn is 3. So this is x to the 3 plus 1 divided by 3 plus 1. And here's the thing. I could write a plus c in here, and I'll go ahead and do that. I'll say plus c1. So there's my antiderivative of that first piece. And then the next piece is we're going to get minus 1/2 times x squared will be x cubed divided by 3, right? I guess since it's the first example, I'll show every little thing. This would be x to the 2 plus 1 over 2 plus 1, plus it has its own constant, we'll call that c2, plus 2 times, okay, here we're looking at the antiderivative of x. This is technically x to the 1 power. And so x to the 1, n would be 1. This would be x to the 1 plus 1 over 1 plus 1 plus, it has its own constant, we'll call that c3. And then finally, we've got minus 4 times, here you have the integral of the dx, right? So the dx is called the differential. So the antiderivative of the differential, those cancel each other out and it leaves just x as the variable. this integral operator cancels with the d operator, leaving just x. However, if you wanted to see this in another way, think of it this way. Dx is really times 1 there, right? When I factored out the 4, that did leave a 1. And so I can think of 1 as being x to the 0 power. And then if we take the antiderivative using power rule of x to the 0, the antiderivative of x to the 0 would be x to the 0 plus 1 over 0 plus 1, which is just x to the 1 over 1, or just x. Which, that's another reason to convince you that the integral of dx is x. Now, we took an antiderivative here, so we would also have a constant here, and I'll call that plus c4. Okay, so let's simplify everything we have at this point. This will be x to the 4th over 4. I'm going to collect all the constants at the end. So this will be minus, you have x cubed over 3. 2 times 3 is 6. So this will be x cubed over 6. Plus here you have x squared over 2, but you've got a 2 that's multiplied. So this is just going to be x squared minus 4x plus, and you have all of these c's. I'm going to group them all together. So all of these constants are arbitrary, which means it could be anything. C1 could be anything. C2 could be anything. C3 could be anything. C4 could be anything. They all could be any constant number, and this answer is still correct. So what we do is we say, okay, rather than write 4 constants that could all be anything, if each one of them individually is arbitrary, then their sum is arbitrary. So C1 plus C2 plus C3 plus C4, we usually just do all of our anti-differentiation in a problem like this, and then at the very end take our answer, which is this, and then add on a single c, which represents the collection of all of the constants that occurred in the problem. So this is the answer that I expect you to give me on a problem like this. And I know this was our first sort of exposure to, a couple of different rules that are going on here. We're going to get some more practice with this. But the main thing that you need to be able to do is honestly do a lot of this in your head. So let me just talk about it real quick. You've got x cubed first, so x cubed would be x to the 4 over 4, right? We've got that. Then you've got x squared, that would be x cubed over 3 times 2, x cubed over 6. We got that. Then you look at 2x, the x here would be x squared over 2, cancel the 2, leave x squared. Minus 4, if you're taking the integral of a constant, it's the constant times x. And then we have plus c, as we've done, collected all the anti-differentiation constants for the problem. I think for most of you, this is going to be the better way to approach these problems, and I don't expect you to show all of this work, but I want you to understand that all of this work does go into producing this as an answer. All right, there were a couple of properties that we were using in that previous example that I want to call out. The first is, this is basically just a repeat of the definition of what it means to be an antiderivative. And that definition is the antiderivative of little f is capital F plus c, assuming that the derivative of the antiderivative gives me back the original function. So this is that definition we saw on page 1. This is just an understanding. 2 and 3. 2 and 3 are linked. They're an understanding of antiderivative or anti-differentiation. And differentiation are inverse operations. So we're used to inverse operations in mathematics. The inverse of multiplication is division. The inverse of addition is subtraction. We're used to thinking about things that cancel other things out, right? The inverse operation of taking a square is a square root. Well, in mathematics, the inverse of taking a derivative, so if you've taken the derivative of little f and you want to undo that, you take the integral. If you've taken the antiderivative of little f and you want to undo that, you take the derivative. Now, only one of these doesn't get you back to the original function, right? If you take the derivative of the integral, you get back the original thing. But here, you don't get back the original thing, you get back f of x plus c. So what we say about this is that it's not completely unique, which can cause us some problems, because most of the time when you take the inverse operation of another operation, it gives back a unique quantity. If you take the number 5 and you multiply it by 2, you get 10. Then if you divide it by 2, you get back to 5. But that's not always the case here. You don't necessarily have a unique answer when you do differentiation and then anti-differentiate it. You don't necessarily get back to the exact same thing. You could get back to a constant addition to that thing. The other operation we used here, and number 4 and 5, I'll link those as well. The antiderivative can distribute to each piece, and you can factor out constants, and you'll talk more about these in Cal 2. But if a operation in mathematics has both number 4 and 5, it's called a linear operation, which means that taking the antiderivative or anti-differentiation is a linear operation in mathematics. That's going to be a more important thing in the Cal 2 course, like I said, but understand it means that we can look at more complicated functions in here and simply distribute the integrals and factor out constants. Finally, 6 is, I don't know that I necessarily need to write this one down, but this is a consequence of understanding what happens with chain rule. This is kind of like a reverse chain rule formula in a sense. So think of it this way. If I told you the derivative of cosine 2x, we know with chain rule, that's minus sine 2x, but then you have to multiply by the 2. So you did the derivative operation to get minus sine, but then you did chain rule to get the times 2. So imagine that you're integrating a function like cosine 2x. Well, you're going backwards, so rather than move forward to negative sine, you're going to go backwards to sine. But if you were to differentiate sine and try to get back to cosine, you would have a 2 pop out just like it did here. So if you have a 2 that would normally be multiplied, when you take the antiderivative, you should instead divide it. And that's all that this formula is saying is the inner function here, ax plus b, its derivative is a. Normally you would multiply by a when you do chain rule, but we're going to have to divide by a when we take the antiderivative. Now this only applies, rule number 6, only applies if the inner function is linear. If it's something other than linear, you'll have to wait for Cal 2 because that's a harder integral formula to take care of. Something called substitution rule that you'll learn about. Also, we're not going to be undoing quotient rule. We're not going to be undoing product rule. So we're going to be looking at pretty simple antiderivatives in this chapter, and we'll leave the tougher antiderivative formulas to Cal 2. You'll spend about the first third of the Cal 2 course leaning into harder antiderivative formulas. All right, so I just want to create a list now of some, based on our knowledge at this point in the course, what are some derivative-antiderivative pairs, okay? So I just want to do it this way. I'm just going to list them one at a time. We know that and here's what I mean by this. We know that the derivative of x to the n is nx to the n minus 1. So that implies that the antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c. That's one formula. So that's power rule. We've already talked about that one. Okay, what about the derivative of an exponential, e to the x? Well, we know that's e to the x. So if I was to reverse that, that would say that the antiderivative of e to the x is, well, just e to the x plus a constant. All right, what about natural log? We know that the derivative of natural log is 1 over x, so that should imply that the antiderivative of 1 over x is natural log. Okay, I'm going to do sine, cosine, and all of those off to the side here. Let me quickly make a circle because this is how we learned it in class. So if I think of this as being the unit circle, then the function cosine is defined here. The function sine has a value of 1 here, minus cosine, and minus sine. And we've said previously in class that if you want to differentiate them, you move clockwise around the circle. So the derivative of minus sine is minus cosine, the derivative of minus cosine is sine, and so on. Now, what if you wanted to do antiderivatives? Well, you just reverse the direction, right? I mean, you're just going anti the direction that we went when we took a derivative in this case. So the antiderivatives of each of these you're just moving counterclockwise along the unit circle. So the antiderivative of sine is cosine. Minus cosine. The antiderivative of minus cosine is minus sine. The antiderivative of minus sine is cosine, and so on. So if you move clockwise, you're differentiating. If you move counterclockwise, you're anti-differentiating. All right. Another function that we looked at briefly is something like the derivative of the arctangent function was 1 over 1 plus x squared. So that would imply that the antiderivative of 1 over 1 plus x squared is arctangent. Let's see here. Another function we looked at. We know that the derivative of a square root, this is just power rule, but in particular the square root we looked at a lot. So the derivative of a square root is 1 over 2 times the square root. So we know that the integral, or the antiderivative of 1 over 2 times the square root, should be the square root function plus c. That one pops up a lot, so it's probably just kind of worth ingraining that. Let's see, another one. We looked at the derivative of not just e to the x, but a to the x for any power a, or for any base a. These are just general antiderivatives. This is natural log of a times a to the x. So what does that mean about the antiderivative of just a to the x? Well, if in taking the derivative you had to multiply by natural log of a, then taking the antiderivative of a to the x, you would think, well, I've got to divide by natural log of a, and that is in fact correct. You divide by the natural log of a. So this is what I mean by derivative antiderivative pairs. We've learned a lot of derivatives in this course, and this is just a short list here. But that automatically means that we know antiderivatives because you just take and reverse this to get back to the original. Now there's some like undoing of constants that has to be done here, like power rule and the example I showed down here. But, just wanted you to understand that's that is one thing that's kind of going on here, is that you've got this pairing between derivatives and antiderivatives. And we're going to use that to our advantage with several examples here. All right, so I'm actually kind of starting you off with a hard one here. 1 over 2 minus 3x. I want you to see this as a 1 over x kind of problem. And we know that the derivative of natural log is 1 over x, right? So, you know, we might think that the derivative of the natural log of 2 minus 3x is useful here, and it is, because the derivative of that function is 1 over 2 minus 3x. But then chain rule says I have to multiply by the derivative of the inner function, which is negative 3. So this is close to this, it's just off by a factor of negative 3. So this makes me think that if I was to take the integral, or the antiderivative of 1 over 2 minus 3x dx, this is really just 1 over x, which is the natural log of that thing. But then rather than multiply by negative 3 because of chain rule, I should divide this quantity by negative 3. And then I have to add c onto it. And so this turns out to be the correct answer. And if you're ever unsure that you've gotten a correct answer on an antiderivative problem, there's a really easy way to check it. So this is my capital F. If this is little f, then capital F is the antiderivative. Here's the way that you check it. You just differentiate the antiderivative and see if you get back to f. So the derivative of this would be the derivative of negative 1/3 natural log 2 minus 3x plus a constant. So that's what I'm differentiating. The derivative of natural log is 1 over whatever's inside it. But times the derivative of the inside, which, as we've already talked about, is negative 3. And then you've got the derivative of the constant c, but that's just 0. And so if you look at what happens here, you have a negative 3 that we divided by, but then you multiplied by negative 3 because of chain rule, and look at how those cancel, leaving you with just 1 over 2 minus 3x, which was the original function. So we checked that the derivative of the antiderivative gave us back that original function, and so this is the correct answer. This is something you can always do to check your answers, but it's this intuition that I'm trying to build here about how derivatives and antiderivatives are related that I really want you to think more along the lines of how we did the problem to begin with. All right, here's another one. This one, you should see this as a e to the x, and you know that the derivative of e to the x is just e to the x. But, you know, you think about it for a little bit and you say, okay, well, if I was taking the derivative of this, then I would have to multiply by a 4 because that's the derivative of the inside. So rather than multiply by 4, I'm going to divide by 4. So the integral of e to the 4x plus 3 would be the same thing, right? Because when you differentiate an e, you get that e back. But rather than multiply by 4, I've got to cancel that, so I'm going to divide by 4 instead. And so this turns out to be the correct answer. I'll leave it to you to check that that is indeed correct, but it is. And honestly, all I'm doing on A and B here is I'm using property 6. Notice that that's all we've done. We've had functions that had linear things inside them, and you're dividing by the chain rule, the derivative of that inner function each time. So all I'm doing is applying property 6 to both A and B. All right, let's look at C. So if I look at C, I've got 1 over 9 plus x squared. I know from what I just looked at a second ago, the pairing that I had, the derivative of arctangent is 1 over 1 plus x squared. So this thing is kind of like this, but I need a 1 here. So it would probably be worth my effort to divide the top and bottom by 9. So let's do that. So this function is divide the top and bottom by 9. It's 1/9 divided by 1 minus x squared over 9, which is 1/9 times 1 over 1 plus, the 9 is really 3 squared, so I can write this as x over 3 squared. So I'm looking at this function, and this function has the form 1 over 1 plus something squared, just like this is. 1 over 1 plus something squared. So I know that the antiderivative of this function is the antiderivative of this function, because algebraically they're the same. I know based on my anti-differentiation rules, if I have a constant, I can factor it out. And I know based on my knowledge of derivative-antiderivative pairs that this is going to be the arctangent of x over 3, right? So I know this will be the arctangent of x over 3. However, if I was doing chain rule, if this is x over 3, this will be 1 over 1 plus x over 3 squared. But I would have to, if I'm doing chain rule, multiply by 1/3. So I'd have to multiply this by 1/3 or divide the whole thing by 3. Well, I am trying to undo that operation, right? This is what the derivative would do. The derivative would divide by 3. The antiderivative, which is what we're calculating now, should offset that, so we should multiply by 3. So this is going to be 1/9 times the arctangent of x over 3, but rather than divide by 3, I'm going to multiply by 3 and add a constant. So 3 divided by 9 here is 1/3. And so all we have to do is check that if we were to take the derivative of this, we'd get back to this function, and I do want you to go in and check that, but this is indeed the correct answer. If you're wondering where the 9 is coming from here, if we go backwards, you know, you've got this 1/9 term out here. You're gonna, if you take the derivative of this, you'll multiply by a third. A third times the third that's there is where it's going to give this 1/9 that's right there. All right, finally this last one. I do not know of any derivative that we've looked at whose function results in something like this. So there's no derivative-antiderivative pair that would be useful here. However, I can do a little bit of algebra and reduce this to just powers. So for instance, this is the same thing as x squared over square root of x plus 1 over square root of x, which is the same thing as, this is 2 minus 1/2. So 2 minus 1/2 is 3/2 power. And this one is a 1/2 in the denominator, so it's x to the minus 1/2 power. So I know that the function given to me here is really just x to the 3/2 plus x to the negative 1/2, which means if I go to take the antiderivative of it, I can just use power rule to do that. And so the antiderivative of x to the 3/2 would be x to the 3/2 plus 1 divided by 3/2 plus 1. Remember, add 1 to the power, divide by that new power. X to the minus 1/2 plus 1 over minus 1/2 plus 1 plus a constant. So this would be x to the 5/2. Then you're dividing by 5/2, which if you flip it means you're multiplying by 2/5. Here you have x to the 1 minus 1/2 is positive 1/2. But if you're dividing by positive 1/2 and you flip that, it's 2 over 1 or just 2. So this would be the answer that I would expect to see on this problem. So be mindful that, anytime you have square roots, roots of any kind, polynomials running around, algebraically you may be able to simplify it to where you can just use power rule on the problem. So just a reminder, the power rule is x to the n plus 1 divided by n plus 1 plus c, and this assumes that n is not negative 1. If n is negative 1, we've got that covered. Negative 1 would be the integral of 1 over x, and we know from our derivative-antiderivative pairs that is natural log. So if n is negative 1, you use that formula instead. So this takes care of all powers of x, including roots, just fine. All right, so let's try this one. This one's a little tricky. We know we've got 1 over square root of something. So we know that the derivative of the square root function is 1 over 2 square root x, right? So we're kind of looking the same. If I wanted to get rid of the 2, all I'd have to do is multiply both sides by 2. So that's looking good. That's 1 over square root, just like this is 1 over square root. Now, if I was to put a 4 minus x inside, this would be 4 minus x, but then chain rule, I would have to multiply by the derivative of the inside, which is negative 1. So I don't have a negative 1 here, so I should multiply both sides here by a negative 1. And there we have it. 1 over square root of 4 minus x is the derivative that results from taking the derivative of this function. So the antiderivative of this, so if you take the antiderivative of both sides, the antiderivative of the derivative, those cancel. Which tells me that this is the result that we want. Now, the one thing that we neglected to put here is a plus c, so don't forget that. So if I was to, all I'm doing is just working backwards with the derivative to obtain the function that's in the integrand here. So I keep working backwards, keep working backwards. This implies this, which implies this, which implies this, which implies it's just a chain of working backwards, understanding what we know about derivatives. So this is negative 2 square root 4 minus x plus a constant. And if you were to differentiate this, you'd get back to this function. All right, we'll do one more here. The integral of 3 cosine x plus 4 sine x over 2 is the integral of 3 cosine x plus the integral of 4 sine x over 2. Factor out constants. All right, so in your head, we're going to do antiderivatives. So we're going counterclockwise on the circle. So the antiderivative of cosine, counterclockwise, cosine goes to sine. And counterclockwise, sine goes to minus cosine. Now, there's one more thing I need to talk about here. We have an x over 2. So normally if you differentiate, like say I'm going to differentiate this, the derivative of negative cosine is sine, but I've got to multiply by the 1/2 and I haven't adjusted for that. So if I would normally multiply by a half or divide by 2, then I should multiply by 2 to offset that. So I claim that the final answer here will be given by this. And, you can do a quick check. So this is the function f of x. Let's do our quick check. The derivative of f is I'll just do it. The derivative of f is 3 sine becomes 3 cosine. The derivative here, -8. The derivative of cosine is minus sine, but you already have a minus. So this is going to be plus 8 sine of x over 2, but then times 1/2 because of chain rule. The derivative of a constant c is 0. So this is 3 cosine x plus 8 divided by 2 is 4. And you notice that you get back what you started with. So that's always how you should check these problems to make sure that you have the correct antiderivatives. All right. Well, up till now we've been looking for general antiderivatives. We've always produced the plus c, but we're going to change that here. I'm going to look for a particular antiderivative on this problem. So suppose I know that we have a specific function in mind, and the function we have in mind has a second derivative given by this function, and I know it passes through the point 0, 1, and it has derivative at 0 of -3. I'm looking for a specific function with these traits. So what I want you to understand is these are what are called initial conditions. And initial conditions allow us to determine particular antiderivatives. In other words, if you want to tell me in particular which antiderivative I'm going back to, then I need more information, and that information comes in the form of telling me which function I'm looking for passes through a specific point or has a specific slope at that point. Here, because it's second derivative, we need 2 pieces of information. If it were just the first derivative, we'd only be going back once, and so we'd only need 1 piece of information. So I'm just going to do the work here and talk about how these initial conditions are used. So we've got the second derivative is x cubed minus 3x squared plus 4x minus 5. And so hopefully you've been picking up on what I've been doing. So let's just go back by 1. The derivative here, so I've taken the antiderivative, right? If you go from second derivative back to first derivative, then you've taken the antiderivative there. Well, let me go ahead and write the notation. So the first derivative would be the antiderivative of the second derivative, because the antiderivative knocks off one of the derivative operations here. So I'm taking the antiderivative of this function. So the antiderivative of x cubed is x to the 4th over 4. The antiderivative of x squared, so I'm looking at the next function, x squared, ignoring the constant for now. X squared is x cubed divided by 3, but I'm dividing by 3 and there's already a 3 there. So those cancel. Here I'm looking at x. The antiderivative of x is x squared. I would divide by 2, but there's a 4 there. 4 divided by 2 is 2. And then finally minus 5. The antiderivative of minus 5 is, remember, if you take the antiderivative of a constant, it's the constant times x. So the antiderivative of minus 5 is minus 5x plus a constant. So there is my first derivative. Now I would need to solve for c. So do I have any information telling me about the first derivative? Well, yeah, I know that the first derivative at 0 is -3. So let's use that. The first derivative at 0 would be, if I plug in x equal to 0, all of those terms zero out, and I'm just left with c. So c must be -3 to fulfill this initial condition. So I know now that my first derivative, the particular first derivative for this function, is given by this. This is my first derivative. Now, we don't want to find the first derivative in this problem. We actually want to do this all over again and go back to the original function. So the original function is going to be the derivative, or the antiderivative of the derivative, which is the antiderivative of what we just found. And I think y'all are starting to get good at this, so let's do this all at once. The antiderivative of x to the fourth would be x to the fifth divided by 5. You already have a 4 there, so it would be x to the fifth divided by 20. Minus the antiderivative of x cubed would be minus x to the fourth over 4. 2x squared, the antiderivative of x squared would be x cubed over 3. You already have a 2 there, so it would be 2 divided by 3x cubed. Minus 5x would be x squared over 2, so minus 5x squared over 2. The antiderivative of negative 3 is negative 3 times x. And then we have another constant here. I'm going to use, since we used c here, I'm just going to say d. I just want a different variable in the problem, so plus arbitrary constant d. Now, in order to find that arbitrary constant, I have to know something about f, and I do. F at 0 is 1. So if f at 0, if you plug x equal to 0 in, it gets rid of all of these, leaving you with just d, so I know that d is 1. And my function is this. So this is finding a particular antiderivative. You have to be given more information, and each time you go back, you peel away one derivative. So you got to go from second derivative to first, find the constant, go from first to original, find the constant. You end up having to find two constants, so you need two pieces of information. This is really getting into the territory of what's called differential equations, which is finding a function that passes through points given the derivative of that function. So you're really getting into what's called baby differential equations at this point. And to just make that very clear, I'm going to do a small differential equations problem with you. So this is the last example for today. We'll do applications of this on Friday. So I want to find the curve whose slope at each point is given by 3x squared, and the curve must pass through the point 1, negative 1. Okay. So I'm just going to write some notation down. If f of x is this unknown function that we're trying to find, then we're told that the slope at each point is 3x squared. So we're told that the slope of this function, which the derivative is slope, is 3x squared. Okay, we know that the function passes through 1, negative 1, so f of 1 equals negative 1. Okay, well that's exactly what we just got through doing up here, right? We're trying to find some unknown function. We're given information about the derivative. The derivative is 3x squared, and we know it passes through the point 1, negative 1. So we're going to work it just like the problem above, but I want to write this in its differential equation form. So a differential equation is an equation that relates some unknown function to its derivative. So in other words, the derivative with respect to x of f of x equals 3x squared, and f at 1 equals negative 1. This is what we call a first order differential equation. And the reason it's first order is because you're taking a first derivative. So the derivative of some function f of x is equal to 3x squared, and we know that f of 1 is equal to negative 1. So it's a first order differential equation. You solve it by taking the antiderivative. So if I have the equation given to me like so. Give myself some room here. Then what you do to solve this is take the antiderivative of both sides of the equation. So if you take the antiderivative of both sides, the antiderivative of the derivative cancels, leaving you just f of x on the left-hand side. And the antiderivative of 3x squared would be 3x to the 2 plus 1 divided by 2 plus 1 plus a constant. So f of x is, you've got 3 divided by 3 here, so it would be x cubed plus a constant. And I know that f at 1, which is 1 cubed plus c, needs to be negative 1. So 1 plus c is negative 1, or c is negative 2. So I know from this line then that f of x is x cubed minus 2. And so congratulations, you've solved your first differential equation. We have an entire course devoted to this topic because there are many different things that happen when you try to solve these kinds of equations. Most of the world can be described in terms of differential equations like this. So it's a very rich course if you get to take the ODE course. And that's, a basic introduction to antiderivatives here. Most of this topic is really going to come down to what I have right here, and it's how well you take derivative formulas that you already know and how easily you compare them with antiderivatives. And really it's just this game of matching a derivative with an antiderivative, and I tried to practice that with you here. Okay? Don't approach this topic as trying to memorize a bunch of formulas. If you do that, you're going to get yourself into trouble. Try to approach this topic as recognizing pairings and then making manipulations to make the pairing work. And always remember that you can go back, just like I did here, you can go back and check your answer by taking the derivative of the answer and seeing if it matches the original function. All right, we'll do more with antiderivatives on Friday, but this should serve as a good introduction to help you start working on some practice problems for the quiz. All right, y'all have a good day. Talk to you later. Bye.